at the end. But you'll recognize the basic idea of this program from our last lecture. We still have our light switch. We're still looking for it to be closed or to be on. Let's take a break from the hard stuff and let's cover a bunch of instructions that are all pretty simple in one big shot. And we'll talk about one that's a little bit more interesting at the end. But you'll recognize the basic idea of this program from our last lecture. We still have our light switch. We're still looking for it to be closed or to be on. And we're still looking at our same counter, count up, and we're counting up to 10 transitions of that light switch going from off to on. Now, as we're flipping that light switch back and forth, we're looking on the following rungs at C5:0.ACC, and that is the address for this accumulator value right here. That's what the ACC stands for, is the accumulator. So as this C50 counter is counting up, it's storing that value in the accumulator. It goes to 1, 2, all the way up to 10, and we'll stay at 10 until we send it the reset command and send it back to 0, or in another way overwrite that accumulator with a different value, which we can do logically, but we're not doing in this program. So for the intents and purposes of this program, there is no reset. There's nothing to overwrite the accumulator. We're just going to count up to 10 every time we flip the switch. And while we're flipping the switch, we've got a handful of light bulbs that are going to be coming on and going back off. And we're going to look at the logic. We're going to look at the comparators being used in the conditions to see why that is. So here we've got GRT, which means greater than. And it's nice enough to explain right below greater than and even show a symbol A greater than B. Then it explains source A and source B. So we've got source A set at our accumulator value for our counter, which is C5:0. And source B, I've plugged in an arbitrarily hard-coded value of 2. So what this is saying is when our accumulator is anything greater than 2, light bulb 1 is going to come on. So we flip our light switch 1 time, no light. 2 times, no light. But once we turn it on the 3rd time, we've got light bulb 1. The next rung down, on rung 2, we have a less than instruction. If you understand the greater than, you understand the less than. If our accumulator is 0, this light is on. If it's 1, if it's 2, if it's 3, light bulb 1, 2 will be on. But once our accumulator reaches 4 or any number greater than 4, our light bulb 1, 2 will be off. Moving down to rung 3, we have GEQ, which means greater than or equal to. And it explains that right below and even shows us the symbol for it. Naturally, we know how that works as well. I have a source B set of 6. If our counter's accumulator is 1 or 2, 3, 4, or 5, light bulb 1, 3 will be off. But once it hits 6 and stays at 6 or anything above, our light bulb 1, 3 will be on. And as much as we have a GEQ, we have an LEQ, less than or equal to. And see, like I said, you're learning a lot of instructions really fast, and these are all easy ones, but don't be mistaken, these are comparative operators that you will be using quite often, especially doing analog programming. So, aside from greater than, less than, greater than or equal to, less than or equal to, we also have EQU and NEQ. Equals, not equal to. So if the C50's accumulator is equal to 1, then light bulb 1,5 will illuminate. And as long as our accumulator value is not equal to 1, light bulb 1,6 will illuminate. So when it's 0, we're lit up. 1, light shuts off. 2 comes back on and stays on all the way up to 10. So we've got greater than, less than, greater than, equal to, less than, equal to, not equal to. And now we have limit. And limit is a very useful comparator, and I'm going to teach you a secret about it that most of your seasoned programmers that have been doing this for quite a while do not know about this instruction. So that's your extra bonus for taking this course. You're going to learn something that the big dogs usually don't know. The way this works, it says here it's a limit test. So we're testing what? We're testing our accumulator value of our counter, and we're comparing it between a low limit and a high limit. So we've got naturally our low limit set at something like 4 and our high limit higher than our low limit. I set it at 7. Now this limit instruction is not exclusive, it is inclusive. And what I mean by that is it's like a greater than equal to combined with a less than equal to. So the accumulator doesn't have to be between 4 and 7. It can be equal to 4 or 7, or it can be between 4 and 7. And as long as that accumulator is 4, 5, 6, or 7, then light bulb 1,7 will be lit up. Now, here's the secret. It's intuitive that our low limit needs to be lower than our high limit, but what if we go and do something crazy, living on the edge, and we switch our low limit and high limit, so now our low limit is actually higher than our high limit? Well, off the top of your head, you would think that's not going to work. That's going to produce an undesired, unpredictable response. The program's going to generate an error, something like that. But actually, this works. And the way it works is exactly the opposite. It's basically reversing the polarity of the limit test. So now, if our accumulator is less than 4, or equal to 4, then our light bulb is going to come on. This limit test is going to pass true. If our accumulator is equal to or greater than 7, it will also be true. But if our accumulator is equal to 5 or 6, this light bulb will be off. So you can actually switch or invert the low and high limits on the limit test, and it will still work. It just works in reverse polarity. And most of your seasoned programmers do not know that little trick. So you now can teach them something that they will be surprised at and say, wow, where did you learn that? And of course you can point the finger at me. We are going to take one more lecture worth of easy instructions before we jump back into something a little more complicated. So now we're going to look at the basic mathematical operators. The first instruction we have on rung 0 is add. Add, obviously, is an addition block. So normally in a program, you would not be adding two constants like this. And actually, if you try to compile this program with two constants, it's not going to work because it won't let you do that kind of math. If you want to use constants, then you don't need to multiply 4 by 3 every single scan. You can just use the number 12 and be done with it. So normally you would have a memory address, an integer, or a float in at least one of these sources. The other one can be a constant, but at least one of these needs to be a memory location. But just to demonstrate, this is going to add 3 plus 4, and it's going to store it as this integer, or I could store it as a float. We also have a subtract block. Obviously, that subtracts source B from source A. So it's 10 minus 6. That's going to store the value 4 in the integer address N7:1. I don't think I have to spend a lot of time on multiply. That works the same way, as does divide, and divides 9 by 3. If you have a decimal and you're trying to force that decimal into an integer, obviously some rounding will occur. If you're storing it as a float, then you may or may not lose much precision. You won't lose much, but if you're using an irregular number, obviously it's going to have to truncate somewhere. Now, if you're doing any kind of halfway complex equation, call it the quadratic formula or something like that, you're going to have several math blocks, one for absolute value, and there are plenty more math blocks than what I'm showing. There's trigonometry, there's one that inverts values, there's several different mathematical operators, most of them just as self-explanatory as these. But the one that I want to call attention to here is CPT, which means compute. This one allows you to put in far more complex instructions, or I should say equations, with absolute values, square roots, factoring, all kinds of fun things. And it does it all in one neat, clean block. So when you're troubleshooting a program, when somebody else is trying to understand your program, they don't have to go back through 20 or 30 of these math blocks to try to figure out what your equation is. It's all right here, one block, doesn't take up space, and it stores the result just the same way these other ones do. The difference is you don't have to take the same value and cycle it through 100 different iterations, or even worse, use 100 different temporary values, all of which require their own location in memory, just to complete one calculation. That's insane. So not all processors have a compute block. Not even all processors that can be programmed with RSLogix 500 accept the compute block. But when it's available, it is a lifesaver. Okay, let's jump back into instructions with one of the slightly more complicated instructions to understand, and it's also one of the more useful instructions, particularly when you're bringing an analog signal in or sending an analog signal out. What this SCP, or scale with parameters, instruction does can be done with a compute block, or it can be done with various other math blocks all used in tandem. But this SCP is a lifesaver, and you will use it extensively with your analogs, so I want you to have a very good comfort level with this instruction. Let me show you how this works. You have several different things to address in here. So the first one, we are going to start with an input. Now that could be a number, that could be a signal coming in from an analog input, but for the sake of explanation right now, we're going to act like we're not dealing with signals or anything. We're just going to use a simple number. So I'm going to put a 2 in. And it's asking me what is my input minimum and maximum. So let's say we've got 2 and we're looking at a scale of 0 to 10. So we're going to put a 0 for the minimum and a 10 for the maximum. Now we're going to be scaling this 2. We're going to be taking it out of a 0 to 10 scale, and we're going to be translating it into a different scale. So let's say we're going to go from a 0 to 10 scale to a 0 to 100 scale. So our scaled minimum is 0, and our scaled maximum is 100. And our output would be saved to some kind of memory location, like an integer value of N710, for instance. Or actually, rather than call that result, we'll call that a scaled value. And what is going to do is this is going to take that 2 as an input, and it's going to save it as a 20 into the memory location N710. So it's taking 2 out of the 0 to 10 scale, and it's translating it to the corresponding value on a 0 to 100 scale, which would of course be 20. Now imagine for a second that we actually have an input coming in, and it's a 4 to 20 milliamp signal. So maybe the value that we have here is 6 milliamps or 5 milliamps, and we're going to put that, let's say we have a 6 milliamp signal, or 6 is our signal coming in, and that's on a scale of 4 to 20. And let's say that analog sensor is a temperature sensor that measures between 32 and 212 degrees. So we would put a 32 here, a 212 here, and whatever that actual temperature is at 6 milliamps would be saved into this memory location. And if we wanted a little bit more resolution, since we're trying to get a temperature on a small range, we would probably want to save that as a float instead of an integer. But we will get into why we would use a float and how that connects to the range and things like that in the next section when we briefly get into resolution and precision. But that is how our scale with parameters block works. It takes a value out of one scale, translates it into another scale. So for that 4 to 20 signal, if we wanted to translate that into 3 different types of readings, one as an integer, one as a float, one on a completely different scale, we could scale that same value 3 different times, saving it to 3 different places and using it for 3 different applications. So when analog programming, SCP, scale with parameters, can and most likely will be your very best friend. All right, let's knock out one quick lesson. This is going to be on the MOV, the move instruction, and this is an easy one. What this does is moves a value from one memory register to another, and technically it really shouldn't be called move. Copy would be more appropriate, but there is a copy command already in the program and it does something completely different. So we're going to go ahead and go with it and roll with the punches, and we're going to say yes, okay, it's called move, but it really doesn't move something from one place to another. It really just imposes that value on a second location. So here I'm moving the source to a destination. My source, I'm just using a constant here, and I'm moving it to t4:0.pre. And if you remember what that is, a T4, that's a timer, and PRE, that's the preset. So If you remember a few lectures back, we were using light sets as an example, and we had a timer governing when lights would come on and when they would shut off. Well, that timer has a preset of however many of this unit, which right now I have it set as a second. So this is a 10-second timer, and that preset I have in here as hard-coded value. But if I execute this program, once this rung executes, it's going to move the value 20 into t4:0.pre, meaning this 10-second timer just became a 20-second timer. So that is one use of the move command. Another one is if you want to reset a value that's being used for math or accumulating days or hours and maybe an hour meter. If you just want to replace that value with a 0 or back to some default value, the move command is probably what you want to use. And there's one other usage of the move command, and that's what's called recasting. What recasting is when you're taking a value from one data type and you're converting it to another one. So in this case, let's say we have an integer value of n70 and maybe it's 25. Well, let's say we want to do some math with that value and change it to something that's going to end up with a decimal point. We won't be able to store that decimal value in an integer. So we're going to move that into a float. And now whenever we do additional math to it, like if we have a value of 7 and we want to divide it by 3, now we can store that decimal and we didn't lose any precision and we didn't compromise the integrity of our calculation either. Likewise, if we have a float and we want to round off the decimals and cast that as an integer, maybe we want to display that on a screen that is going to be for an operator who doesn't need to see a decimal, we can cast that float right back into an integer and display the value, and going back and forth between float and integer creates kind of a tricky method for limiting the precision of a float. So if we want a float that only has one decimal point, then we can multiply by 10, store it as an integer, divide it back down, and put it back into a float, and now we have a 0.1 or a 0.7 or something along those lines. So by going into an integer, multiplying by 10, and then coming back into a float, we can effectively round to the tenths place or to the hundredths place if we want to multiply by 100, and so on and so forth. So there are definitely some instances where you'll have to do something like that and recast an integer as a float or vice versa, and the move command is good for that as well. Well, let's look at one more slightly complicated instruction set, and right now we're going to be looking at the jump and label JMP and LBL instructions. And what these do is they allow the program to jump around instead of flowing normally like it does from top to bottom. So here's an example. We've got our light switch right here on B300 again, and we're looking for that to be closed. If it's closed, if it's in the on position, then our light bulb 1-1 is going to illuminate, and on this second branch we're going to jump to location Q20. Now any jump is addressed with a Q. The 2 has to be whatever ladder you're jumping in, and each label has to have its own number 0, 1, 2, 3 up through 15. So here we're jumping to program file 2 label 0. So we're in program file 2, which is easy because we only have one program file, and here's label 0, which is also easy because we only have one label right now. So if the light switch is on, then the light bulb is on, and when we scan this rung, we're going to jump straight to label 0, and we're going to keep executing from there. You notice we're going to be skipping rung 1 when we make that jump. And rung 1 has a horn bit attached to it, so we're assuming that's connected to a loud, annoying horn, which is going to get our attention anytime this light switch is off. Because if this light switch is off, the light bulb isn't going to be on, and we are not going to jump. Instead, we're going to go right down to rung 1 and sound the alarm. Then we're going to come down to rung 2, and we're going to jump to our label. Now, here's something strange about a label. If you have a label on rung 3 with whatever instructions here, you cannot execute this rung unless you jump to it. In other words, if you have a label on this line and there's no jumps anywhere on your program, it will never execute rung 3. It will go from 2 straight to 4. So in order to ever execute a rung that has a label, you must jump to it, which means you'll have your jumps and the logic that's possibly going to be skipped depending on the conditions above, but usually right before your label rung, you'll have a jump rung just in case nothing above happens to jump to it. Then as a last ditch, even though there are no conditions, you'll go ahead and jump to that rung unless it's something that you only want to execute under certain conditions. But that is the tricky part to remember the first time you're programming with jump and label, is everybody always puts in their jumps, puts in their labels, but forgets that the labeled rung will never execute unless you jump to it. So they have all these jumps with conditions, but they don't have a jump all by itself. So if none of the rungs with conditions are met, this line with whatever instruction might be to the right will never execute. So very important to remember that if you're using labels, you must jump to that line or it will never execute. Welcome to the last lecture of this section, and I know this has been a big section and a lot of material in here. Arguably, you could say that this is the heart of the whole course, and we're certainly going to go out with a bang. This last instruction that we're going to discuss is very important if you're doing any kind of very sensitive, very critical analog process control where you have to control an output to a very specific set point without a lot of drift and oscillation, rise and fall, things like that. So this is the PID control. PID stands for proportional integral derivative, and this is the math behind the instruction. So at a glance, unless you remember your calculus, this is not pretty, it's not easy to understand, and as difficult as it is for a programmer to understand, it's far more so for most of the programmers' customers, the machine operators at the end. So this is what is happening with this program and how this works, and I am not going to be able to give you a comprehensive understanding of the PID control in this course. The main reason being there are entire courses built around nothing but the PID control. There are $1,000 software packages that do nothing but make adjustments to the PID control. So what you should take out of this is the basic understanding of what it does and how it works when you need it. And you've got a lot of independent homework to do before you're probably ready to implement and tune a PID. But let me introduce it and let me explain it. Here, we're using a scale with parameters, and you see this address I:4.0. That is our imaginary input, and all of our inputs are going to begin with the letter I, just like our outputs are going to begin with the letter O. So we have an input signal, and based on the input minimum and maximum being 4,000 and 20,000, that tells us that we're working with a 4 to 20 milliamp signal. And why that comes out to 4,000 and 20,000 I will explain in the next section. So bear with me, and except for the time being, it really is 4,000 to 20,000. We're going to be scaling that to a range of 0 to 16,383. And if you don't already know resolutions and powers of 2 and bit depth and things like that, that number is going to seem very arbitrary and very strange. But again, next section, that number will come home and make a lot more sense to you. So right now, we're scaling this input signal from 4 to 20 to 0 to 16,383, and we're storing it in the integer location N70. Now, our next rung 1, the only thing we have happening here is our very unassuming, innocent-looking PID control. But we're going to see just how complicated and crazy this thing really is. We are storing it to PD, which is our type of data file over here. This is one that I had to create. So I created this PD22 and set it up for our PID control. And we have a process variable and a control variable. What a PID does is it receives a set point. That can be a hard-coded value, but more likely that's something that comes from an operator. That value tells it what set point it should try to maintain on the control variable and the process variable. So what this control looks at is N70, which is set up right now as its process variable. It looks at that and tries to adjust the control variable to make the process variable line up with the set point. And when we look inside the setup, we've got inverse or directly proportional control modes, whether our PID control is auto or manual. There are ranges as far as if we want to limit our minimum or maximum output, what our scale values are, our set point. There is just a whole lot going on inside the PID, and most of the adjustments that are going to dictate how this works occur on the KC, TI, and TD, your gain, reset, and rate. There are so many techniques, so many programs, there are so many different ways to tune a PID loop to keep it from oscillating, to tune it to maintain a set point accurately and correctly, and it's a course in and of its own. But right now, aside from being exposed, seeing it laid out in a program, and I want you to have a general idea of what the PID does and when you'll need it. If you are controlling a motor and its speed needs to be very precisely 2400 RPMs, and you have a tachometer sending you an analog input signal and you're sending an output to a motor drive, you can't afford for that motor to be oscillating up to 3,000 down to 2,000 and waving back and forth. It's going to destroy the drive, the motor, and probably your process as well. In that case, you're not going to be able to use simple logic to control that drive. You're going to have to use a PID control. And in that case, again, you're going to have some homework to do, but I want you to know that's the control you need to go to. That's the process that you're going to have to work through in order to tune that. And without being hooked up to a live motor with a live input signal coming in, you're really not going to be able to tune that loop. Even the emulators that are made by Rockwell, the same company that makes this software, the emulators won't even execute a PID control. When you run the PLC program through an emulator, it just ignores that PID and won't start it, not in manual, not in auto. So it's not the friendliest, easiest command to use, but when you need it, there is no substitution, there is no imitation. That's really what you have to use. And getting them set up right is never simple, particularly when the process is something very precise. So with that, I'm going to step away from the instruction, and we're going to get into a little bit more details on considerations and other aspects of the PLC programming process. But with the instructions that we've covered in this section, you're going to be able to do 90 to 95% of everything you need to do behind